Hello, I am Dr. Miller, Math Magician. Today, I hope to impress you with what you're going to learn about fractions. To give you an idea of what we're going to be doing, we're going to first define a fraction, as silly as it may seem. Then we're going to talk about proper fractions with slightly different terminology than we think of them normally. Then we're going to talk about adding fractions. And one of the questions we're going to ask is, why don't we add the denominators when we add fractions? Next, we're going to talk about multiplying, dividing fractions, but more important, we're going to tell you how the rules come about. This is something we found interesting. A lot of people just accept them. And then we'll talk about adding, reducing fractions, and the importance of prime numbers in this process. And then we'll talk about mixed and improper fractions. And finally, we'll end with how we apply these. And you're going to find some very interesting applications and some very interesting surprises. So come on this short journey with fractions with me and see what you can learn. So what is a fraction? Let's start off with division, which is really reverse multiplication. So if 3 times 2 is 6, 3 is equal to 6 divided by 2, or 2 is equal to 6 divided by 3. But we get a very interesting question when we say, what multiplied by 3 will give us 2? And if we search for an answer, we'll find out that it's 2 divided by 3. But that's not an integer. You also note that there are 2 ways of writing it. Both of them have the same meaning. One is just a different notation. So let's start off with multiplication. By multiplication, we say that if we have 3 5s, we just add them together. And it's important. They have to be all 5s. They can't be 2 5s and a 6, or 5, 6, and 4. Now we make a discovery. 5 times 1/5, where 1/5 is a fraction, is going to be 5 of these. 1, 2, 3, 4, 5. And we define a fraction by saying that these will add up to 1. And now we're ready to define a fraction, or what I call a unary fraction. Is that when a fraction, denoted by this symbol, multiplied by the number in the denominator, it will give us 1. So when a fraction is multiplied by the inverse, it will give us the unary number for multiplication. I have also invented my own notation because when I've worked with negative numbers, I found that you put a minus sign. So I've decided to just leave the 1 off and use the slash as the fraction. So now, a unary fraction is defined such that when it is multiplied by its inverse, the denominator, we get the identity element for multiplication. These are classic mistakes. What is a month? It's not a 12th of the year, as almost everybody in the class will say, because multiplication assumes all the parts are equal. That's what we did with the 3 times 5. January has 31 days. April has 30 days. All the months are not equal. What about a week? A week is not a 52nd of the year, because if we multiply 7 times 52, we get 364. And we want 365 out of 365 days, not 364 out of 365 days. So the product must come out to 1. What about if we cut $1 into 100 pieces? One of those pieces is not a cent. It's a piece of confetti. A part of a whole is not the correct definition for a fraction. So these are classical mistakes to just mislead us. Now this is going to take us a little time for this chart. It is important that we know our basic operations. Associative property, which is grouping. Commutative property, which is ordering. Identity property for addition is 0, and for multiplication it's 1. The distributive property is how we define the multiplication and addition numbers. And the transitive property is replacing something by its equal. I don't want to spend time on this, but it's really important to know these. I often call this acid T, taking the acronym from the letters. Kids should know this by the 3rd or 4th grade. If not, they're just memorizing their way through mathematics without understanding what's going on. So let's start off with our definition. We'll use 3 as our example. 3 times 1/3 is 1. And then we note that if we use the division as reverse multiplication, that 1/3 is the same as 1 divided by 3. And very often kids will give me a sort of correct definition. Fraction is a division. 1/3 times 6 is 2, and 6 divided by 3 is 2. So, but we really want to get a feel for that. And that's one of the things we're looking at, is to get a feel for this so that we really understand what's going on. So what I'm going to show you is something else interesting in fraction. If we start off with 3 times 1 is equal to 3, and then we divide both sides by 7, and then group the 1 divided by 7, we could replace that by a fraction, because that's what a division is. 1 divided by a number is a fraction. So 3 times 1/7 is the same as 3 divided by 7, or 3/7, which we call as a fraction. And so we're noticing that a fraction can be written as a multiplication of its numerator times the unary fraction with the denominator. This is an important concept. Simple as it may be, but this is where we want to focus our attention. 3/7 is the same as 3 times 1/7. Okay. Because this is so important, I want to spend more time on it. 3/7 is usually read as 3/7. It could also be read as 3 divided by 7. But what is important that we notice is that 3/7 is also the 3 times 1/7, or 3/7. This is my notation, where I just leave the 1 out. And then if we just commute them, 3/7 is also the 1/7 times 3. Just think of 1/7 as just another element, as one would think of an integer as another element. Now, if we call this object here a whole, then 1/7 is this little piece here, because if we take 7 of them and put them in there, it'll add up to this whole piece. If we filled in 3 of these, we have 3/7. 3/7. This is the way I'd like to think of this, as opposed to just 3/7. So remember, if we think of this as a fraction, it's going to help us understand fractions much better, looking at it as this part. Now, here's where our first test comes for the use of fractions. If we want to add 1/7, 2/7, and 3/7, what we've been taught is, if the denominators are the same, we just add the numerators. And the answer would be 1 plus 2 plus 3, or 6/7. But why? Well, remember, 1/7 can be written as 1 times 1/7, 2/7 can be written as 2 times 1/7, and 3 can be written as 3 times 1/7. And what we have in here is a common factor, 1/7. And using the distributive property, this could be written as 1 plus 2 plus 3 times 1/7. Because the distributive property says when we multiply something times a group of additions, we multiply it by each one and add them together. But 1 plus 2 plus 3 is 6. And we know that 6 times 1/7 can be written as 6/7. Now, we don't want to have to go through this every time that we're doing addition. We do it the way we were taught. We just add the numerators. But now we understand why, and we understand why the denominators have to be the same, because of the distributive property. Now, a lot of people like to use manipulatives. Later on, we're going to see in one of the applications where manipulatives don't give us a full answer. Manipulatives should use to be verified. As I did with before when I showed you this 7/7. I used rectangular tiles to illustrate how fractions work. But a manipulative is just one application. What happens when we go to applications which are not mappable onto the manipulative that we used? Now, on the last sheet, we showed you a proof. We gave you a step and we explained that step. Now we're going to look at multiplication and division, and this is a rather crowded sheet. Remember, we start off with our basics, the definition of a fraction, and that we can show that a fraction is the same as a division. We also note the power of the associative property. 35 times 1 over 35 is the same as 1 divided by 30, is the same as 3 times 5 times 1 over 3 times 5. So 1 over 3 times 5 is the same as 1/35. Now let's begin. This side and this side are the same, with just one subtle difference in terms of what we commute. So we take the definition of fraction twice. 3 times 1/3 and 5 times 1/5 is 1. And then we just interchange the 1/3 and the 5 to get our integers and fractions together. That's the commutative property. We now associate which multiplications we're going to do first, and we get our integers times our fractions. And now we use division. Just bring this over the other side, and 1/3 times 1/5 is equal to 1 divided by 3 times 5. But from this property over here, we know that 1 over 3 times 5 can be written as a fraction. So we now see we're multiplying the numerators in order to get the answer. The second part, we go through the same process, except that we don't get the integers or the fractions together, we get them sort of mixed. Again, we remember that 5 times 1/3 can be written as, we remember that that this is equal to this divided by this, and so we get 3 times 1/5 is 1 divided by 3 times 1/3. But remember that instruction we said this can be written as 3/5, that can be written as 5/3. And now we see why we invert fractions. Basically, it's the definition. Once that definition, the rules follow. And mathematicians just love to make up rules. Sometimes the rules are practical. We use them in some problems. Okay, and then if we continue this, if we multiply this expression by 2 times 7 and went through the process, we would now see that we're multiplying the numerators times the denominators. So now we know why we multiply the numerators and denominators, but we only add the numerators when the denominators are the same, and they must be the same in order to be able to add them because of the distributive properties. At this point in time, we could let you figure everything out. But let's just look at some of the other applications you have with fractions. Again, let's go back and remember that a fraction 7 times 1/7 is equal to 1, which can also be written as 7/7. Okay, so if we want to add 2/5 plus 3/7, different denominators, we have to make the denominators the same if we can add them. So I'm going to multiply each one by 1. That's the identity, it doesn't change things. But 1 can also be represented by 7/7 or 5/5. So I've used the denominators in an alternate fashion. Now the rule says I multiply numerators and denominators, which I now do. And then I realize that now I have the same numerator, 5 times 7 or 35. So I just add the numerators, and this gives me this, and then doing the multiplication, I finally get my answer. So this definition of fraction is coming back again. The notation for what a fraction keeps coming back again. Those are the things we need to emphasize. And if we want to reduce fractions, we just factor this into their prime numbers. So 60 can be written this way in its prime numbers, and 72. And then we just pair them off, and we see 2 halves, 2 halves, 3/3. When these are all multiplied, it gives us what we have there. But this is 1, this is 1, and this is 1. And so we're left with 5/6. Okay, so what happens if we get something like 3 1/7? Okay, 3 3/7 really means 3 plus 3/7, number structure-wise. Okay, and so we know that 3 can be replaced by 3 by 1 because we looked up here, if 3 times 1 is 3, then by division, or reverse multiplication, 3 must be equal to 3 divided by 1. Okay, doing that, we now have to get the denominators the same to add them. So we make use of that 7, multiply this by 1. So that's still the same. Multiply the numerators and denominators. Now add the numerators, and we get 24/7 is the same as 3 3/7. So once we know those basic rules, now it's just a question of finding examples to apply to them. Okay, let's apply what we learned. I want to multiply 3 2/7 times 7 3/7. One common mistake kids will make was they'll multiply the 7 times the 3 and get 21, and multiply the 3/7 times the 2/7 and get 6/49. Because in adding, you would add the integers and you would add the fractions. But we have to remember the distributive property. And so if we use the distributive property, what we have to do is multiply the 7 times the 3, the 7 times the 2/7, which gives us 2. And then we multiply 3/7 times this, which gives us 9/7, which is the same as 1 2/7. And 3/7 times 2/7 is 6/49. I can do all this in my head. It's simple. Okay, then I add them. 1 plus 2 is 3, plus 21 is 24. 2/7 is the same as 14/49. 14 plus 6 is 20, and I get 20/49. This is the way you were taught in school. You first convert these to improper fractions. These two numbers are too big to multiply, so you have to do the multiplication. And then it's hard to divide 49 into this, so you have to again do this with long division. This is very prone to error and takes lots of time. I've done it both ways, and most of the time I make a mistake on this way, and it takes me 2 or 3 times longer. So what happens is we begin to understand, we discover these things in the same way I discovered this for myself. Now we're going to make a discovery. One of the reasons why, where we find that there's more to math than we sometimes see. Now instead of applying this to linear or numbers on a line, let's apply this to a clock, numbers in a circle. That's a practical application of math. Basically we define how the rules work, but it's the same set of rules, commutative, associative, distributive. On a clock, 12 o'clock, we go around the clock twice, or a second time, it's still the same place on the clock. 3 times around, it's still the same place on the clock. 4 times it's around the same place on the clock. So if I decide that I want to multiply 1/4 times 8, 8 around the clock once is the same, 8 around the clock twice is the same, 8 around the clock 3 times is the same. Okay, so 1/4 of 8 is 2, 1/4 of 20 is 5, 1/4 of 32 is 4, and 1/4 of 44 is 11. 4 answers. Not one answer, but 4 answers. Okay, so let's check it. 2 times 4 is 8, 4 times 8 is 32, but we subtract twice around the clock, and that gives us 8 again. 4 times 5 is 20, we subtract once around the clock, and that gives us 8 again. So what we see is, it checks out. Now, fractions can also be used for exponents. Still away from those manipulative examples we were given. So 6 times to the raised to the 1/4 power is the same as 16 times this number here, e to the 2 pi I, which is equivalent to 1. And when you take n and let n go from 0, 1, 2, 3, etc., we end up getting e to the 0, e to the pi over 2, etc. And if we know something about complex numbers, this is 2, 2i, minus 2, and minus 2i. And if we multiply each of these together by itself 4 times, we will get 16. What's interesting is this modular concept shows up in the exponents as well as in the clock. This goes beyond the basic fractions you're taught. So we have to be careful how we use the manipulatives if we want to be able to really express ourselves in the work we do. Okay, taking notes is important. What I wrote down, you should be taking those notes, and then it would be nice to have a copy after you're finished. But summarization is important, and summarization is part of the studying process, where we review what we have so we can put it in a concise step. So first we talked about the importance of the basic postulates. These set up the rules, and these rules, they're based upon observation. Okay, all operations are not necessarily commutative, as we saw with division and we would see with subtraction. Knowing definitions is important. Okay, proving the rules lets us understand what we're doing and makes it easier to retain what we've learned. Okay, I found my own personal experience, I could study twice as fast or in a quarter of the time that my classmates did and could do better on the exams, because I could always derive the formulas if I forgot them. Okay, it also made it easier for me to retain the information because I would practice it so much. Manipulatives should be used for validation. Okay, understanding leads to discovery. Understanding is thinking. And finally, we summarize the things that we just proved.